Let's look at an extremely tedious example using a power lowering formula. So I want to write this expression in terms of the first power of cosine. So the first thing I would do is write each of these in terms of squares. So sine to the fourth of x is sine squared of x times sine squared of x. And then I've got my cosine squared of x. And these are all multiplied, don't forget. Sine squared of x, as we well know, is 1/2 times the quantity 1 minus cosine of 2x. And then I need that again for my next sine squared. And cosine squared is 1/2 times 1 plus cosine of 2x. Don't forget that the 1/2s here are being multiplied as well, so if you wanted you could put dots there, and they've got 6 things multiplied, and so we can rearrange the order here however we like, and 1/2 times 1/2 times 1/2 is 1/8. Okay, then I need to multiply the 3 binomials together. By the way, the reason we know we need to do that, each of these cosines is to the first power, right? And it says write it in terms of the first power of cosine. However, we have to consider that all of this is multiplied. So if I were to multiply this binomial by this binomial, I would get a cosine squared out of this, and I'd have to reduce that power. So I need to keep multiplying and keep reducing powers as I go. Now I need to multiply all 3 binomials together. I can do that in any order that I want. So I am not going to multiply the two 1 minus cosine of 2x's together first. Okay? I'm going to be a bit more strategic and multiply with this 1 minus by its conjugate 1 plus, because those multiply very nicely. Okay? So when I do that, I'm going to multiply these two together now. That is simply 1 minus cosine of 2x times cosine of 2x. Well, that's simply cosine of 2x squared. So cosine squared of 2x, right? Multiply something by itself, it's squared. And so, since they're conjugates, there's no middle term when I multiply the binomials. So those two things yield this, and that's it. And then I'm just going to recopy my 1 minus cosine 2x down here. Now, this guy is cosine squared. So let's reduce that power first before I do anything else. So I've got 1/8 times 1 minus 1/2 times the quantity 1 plus, because this is a cosine squared, 1 plus cosine of the angle double, so it becomes a 4x. And now this is what that first set of parentheses was, and I'll recopy my 1 minus cosine 2x. Now what I'm going to do is try to make all of this as simple as I can before I try to multiply this stuff by this binomial. So the way to do that is to distribute this negative 1/2 through. So I've got 1/8 times 1 minus 1/2 minus 1/2 cosine 4x. If that's still what's in here, then I'll just recopy my 1 minus cosine 2x. Okay, we're getting closer. 1 minus 1/2 I can actually combine and get 1/2. So I have 1/2 minus 1/2 cosine 4x, and here I have 1 minus cosine 2x. Okay, now this is a binomial, this is a binomial, we could multiply those, but I'm going to take it one step further to make our lives even easier. There's a 1/2 that's common to these, so what I'm going to do is factor out the 1/2 that's common, and when I do that, the 1/2 is going to multiply by this 1/8 to give me 1/16. Factor a 1/2 out, I get 1 minus 1 cosine 4x, or just 1 minus cosine 4x, times 1 minus cosine 2x. Okay, now I've got this looking pretty simple. So I'll multiply these two binomials. So I distribute my 1 through both of these guys. So I have 1 times 1, then I have 1 times negative cosine 2x. Then I'll distribute this guy through both. So I've got negative cosine 4x times 1. And I've got negative cosine 4x times negative cosine 2x. That's positive cosine 4x cosine 2x. I can't combine those. I can't make that cosine squared because they have differing angles. Now, the only thing left to multiply is to distribute my 1/16, but that is not going to yield any higher power of cosine. This is cosine to the first, cosine to the first, cosine to the first, cosine to the first. So we've met the requirement that everything's in terms of the first power of cosine, and we could stop. Or we could distribute the 1/16 and then call it a day.